Now I want to talk about the formula for Laplace transformation of f prime of t. For this, let's assume that we denote the Laplace transform of the original function as capital F of s. By the way, this is actually pretty customary. Whenever you try to transform a function of lowercase letter, you write its Laplace transform as uppercase with the variable s. That's a customary thing. You're going to see how that convention is used when we use Laplace transforms to solve differential equations, right? Okay. But let's just say this is true. That's our assumption, given. Now let's see what this given means. It means that f of s is the integral from 0 to infinity of e to the negative st of ft dt. That's what it means. So if we're given this, let's try to figure out what that gives us. Okay. So Laplace transform of f prime of t is by definition 0 to infinity of e to the negative st of f prime of t dt. That's what you get by definition. And what you want to do is you want to do integration by parts. Now, let me show you the integration by parts in two ways because we're so used to the tabular method. Maybe if I do the original integration by parts, it might throw you off. But let me show you the integration by parts in the original way first. So you take u as e to the negative st and dv as f prime t dt. Now, what do you get if you differentiate? If you differentiate e to the negative st, what happens? Negative s comes in front. So we get negative s e to the negative st. And if you integrate this, you get v equals to f of t. And using the formula integration of u dv is equal to uv minus v du, it says this integral is same as u times v, which is this times that, e to the negative st times f of t. And you have to plug in the endpoints. Okay. Then minus v du. What is v? This is v, and that's du. So it's minus, oh, sorry, this should be dt here, minus 0 to infinity of negative s e to the negative st ft dt. Now we can get the same result by applying the tabular integration. After all, when I introduced the tabular integration to you guys, I said anything you can do with integration by parts, tabular can do. Okay, it's just anything you can do with tabular, you can do it by integration by parts. They're just different way of writing down the same thing. So if I do it using the tabular, here's how you approach it. Plus minus d integral, you differentiate e to the negative st, and you put f prime of t. And notice how we apply the integration by parts just once. That means you just go once, right? So if I differentiate, it's negative s e to the negative st, and if we integrate f prime of t, we get the original function, because if we integrate what was differentiated, we recover what it was. And you have plus or minus, and multiplying these two, we get e to the negative st ft, just like how we had here. This is recovered right there, okay? And then we have to multiply the last row and integrate, right? Negative times negative is positive, so you have to do s e to the negative st ft dt, and you have to integrate from 0 to infinity, which is exactly the same as that. We just made these two as pluses, okay? So either way, you're going to get the same result, whether you use the traditional use of integration by parts or the tabular integration. You get this as a result. Okay, now let's think about this. What do you get if you plug in infinity to this? E to the negative infinity, that's 0. So you're going to get 0 when you plug in infinity. Of course, you have to assume something about the function f. But that's always assumed. F can't be growing too fast. It'll always be manageable so that this will end up being 0. So when you calculate this, we get first 0. Now, what do you get if you plug in 0? E to the 0th power is 1, and f of 0. These are values of t, right? You're not plugging them into s, you're plugging into t. So when you plug into this t, you get f of 0. So you get 0 minus f0 from the first one. And then if you look at this, s has nothing to do with this dt, so that can be considered as a constant which can be pulled out. So I can pull it out and write it as s times integral of 0 to infinity of e to the negative st f of t dt. Wait, what is this? It's f of s, capital F of s. Therefore, you get capital F of s times s minus f of 0. So that's the important formula that we just figured out. We just proved that if you take the Laplace transform of f prime of t, you end up with capital F. No, you end up with s times capital F of s minus small case the 0 value of the original function f. Okay. And that's the proof. Do you have any questions? All right. And in fact, we're going to use this many, many times when we try to apply the Laplace transform to solve differential equations. Okay. Now, let's try to see what this means for Laplace transform of f double prime of t. Well, see, f double prime of t is the derivative of f prime of t, isn't it? Right? So I can pretend that I have the derivative of f prime of t and apply the above formula. The only difference is, instead of putting f of s, we can't use capital F for it. So having lack of anything to call it, we will just call it like this. Okay? Because this formula can be also thought as the following: it's Laplace transform of f prime of t is s times the Laplace transform of the original function minus f of 0. That's what this formula is saying, because capital F of s is after all this thing, right? So if you apply this formula to what we have over here with f prime of t replacing f of t, then this will be f prime of t, and that's f prime of 0, and this will be derivative of f prime of t, which is f double prime of t. So this is what you get. But then you see this and say, hey, this I know what it is. I can apply this one, right? So I get s times f of s minus f of 0 minus f prime of 0. So you get s squared of f of s minus s times f of 0 minus f prime of 0. And we can play this game on and on. For example, what's the Laplace transform of f triple prime of t? Now, if I apply this formula, what should I write? Help me out here. I want to apply this formula. S times Laplace transform of f double prime t minus what? Okay? But what is this? I found it here, right? So we get s cubed f of s minus s squared f of 0 minus s times f prime of 0 minus f double prime of 0. Okay? So now do you see a pattern? Can you guess what the next one will be? What would it be if I take the fourth derivative of f? S to the fourth, fs, s to the third, f of 0, s to the second, f prime of 0, s times f double prime of 0, minus f triple prime of 0. Okay? So it's like this. No derivative to the third. 0 plus 3 is 3, right? 1 derivative, 2. 1 plus 2 is 3. 2 derivative, 1. 1 plus 2 is 3. S to the 0th power, 0 plus 3 is 3. Okay, so if you count the number of derivatives and multiplication of s's, they always have the same number, 3, 3, 3, 3, 3. Okay? And then if you differentiate 4 times, it's s to the 4th. Right? If you differentiate 3 times, it's s to the 3rd. If you differentiate twice, it's s squared. Okay? All right. So we have these formulas at hand. And now let me explain why Laplace transform is desired. Laplace transform is a wonderful tool in solving differential equations because if you had, for example, y double prime minus 5y prime plus, say, 4y equal to cosine of 3t. Let's say you have this differential equation with y of 0 being 1 and y prime of 0 being 0. Suppose this is what you had. Now the idea of using Laplace transform to this is to apply Laplace transform both sides. So apply Laplace transform both sides. So on the left, and on the right. Now, this is Laplace transform of y double prime, so I can use this one, right? So what does that give me? S squared. Now, the Laplace transform of y will be called capital Y because of our convention of calling, using the capital for the transformed function. Okay? Minus s times y of 0 minus y prime of 0 minus 5 y prime. I have the formula here, right? So it's s times capital Y of s minus y of 0. And then finally, on the right side, there's a formula for cosine 3t. What's the Laplace transform of this? It's s over s squared plus 3 squared. Okay. And I can even replace what y of 0 are. Y of 0 is 1, right? So I have s squared y of s minus s. What's y prime of 0? That's 0. Minus 5 s. Oh, sorry, I forgot the last one. 4 y of s. Sorry about that. I forgot that one. So coming back here, y of 0 is 1. Negative 5 times negative 1 is positive 5 plus 4 times capital Y of s equal to s over s squared plus 3 squared. hopefully my 5 looks different from, this is 5. These are 5s. The remaining things that look like 5 is really s. Okay. All right, so this is what we get. Do you see any derivatives? I don't see any derivatives. So what kind of equation is this? Just an algebraic equation, right? Can you solve for y of s? Of course you can. If you took junior high school algebra, you can solve this for y of s, right? So that's the big deal. The reason you want to use Laplace transform is if you apply the Laplace transform, suddenly differential equations turn into algebraic equations. Now, but it's not all utopia here, because even after solving y of s, you still have to figure out what it was. So you have to do the inverse transform. So looking at the function that you get, you have to figure out what your original function is, and that's actually the painful part. Okay. But still, it does something that you weren't able to do before. That's why we want Laplace transforms.